Hello, everyone. Welcome back. So today's topic is going to be subunit 1.5, which is all about atomic structure and electron configuration. So a lot of today is going to be review with a little bit of new stuff at the end. So let's get started. All right, so to start off with, this image in front of you, which is a little pixely, I apologize. This is a model of the atom called the Bohr model, which isn't necessarily the up-to-date model. It's not necessarily the model that's used today. However, it gives us a pretty good understanding of the model of how the atom is organized. You guys will remember you've got positively charged protons in the nucleus. You also have neutral neutrons in the nucleus. And then these blue particles, those are to represent your negatively charged electrons that are moving around on energy levels. The only part of the Bohr model that isn't quite correct with what we know about the atom today is that although electrons do travel around the nucleus, they're not locked into these orbits like this picture is showing, but it's a pretty good approximation, so we're going to use it. So the first thing we're going to go over today, which is really review, is do you remember how to describe where an electron is located? So do you all remember your electron configurations? Do you remember 1s2, 2s2, 2p6, 3s2, that whole thing? And if you took chemistry at Oakton, we color-coded our periodic tables back in Chem 1. If you guys will recall, anywhere that is colored red, this was to represent the S sublevel, yellow was the P sublevel, P, yellow, I'm a child. Anyway, the green area, the transition metals, that was your D sublevel, and the area at the bottom, that was your F sublevel. And if you still have that color-coded periodic table, great. However, I would caution you against using your old periodic table too much because you're not going to be using that one on the AP exam. So you want to get used to the new periodic table that you have for AP as much as possible. However, your copy of the AP exam or of the AP periodic table is yours. You can write all over it. And one thing you might want to write on there, you should have numbers running down the side already, 1, 2, 3, etc., etc. But some numbers that I might recommend that you add would be, and I'm going to try to write this as best you can so you can see it. I would recommend putting a big number 3, 4, 5, 6 on that junction there. And then over across where the green meets the yellow, 4, 5, 6, and I think your periodic table has another row, you would put 7. Down here at the bottom, let's put next to the F sublevel a big number 4 and 5. If you will recall back from Chem 1, those numbers represent energy levels. So what I want to do is just kind of review with you guys a little bit, see what you remember, and then I'm going to let you guys do some practice. Okay, so I'm just going to pick some elements here. Let's do, I'll put a little X in the box I'm referring to. Let's do the electron configuration for the element sulfur, which is right there where I've put that X. So remember, we do electron configurations just as we read in English. We start at the top left corner and we read left to right, top to bottom. So we're going to start right here and read across. So we go 1s2, 2s2, then I'm here, 2p6, 3s2, then I'm here, 3p, 1, 2, 3, 3p4. Okay. If you guys will remember, there's also a shortcut, which I'll remind you about in just a second. So let's do 2 more examples, and then I will remind you about this shortcut. Okay, and I'm sorry, I pushed the wrong button and it erased my numbers that I had drawn on there, but hopefully you have them written on yours. So let's do another example. Let's do the element, let's do titanium, which is located right there in the transition metals. Okay, so again, all electron configurations are going to start the same. So it starts out 1s2, 2s2, 2p6, 3s2, 3p6. If you're following along with me, I'm at this point, I'm right here. 4s2, be careful, 3d2. Okay, we will talk in just a little bit about why the electron configuration goes from 4s to 3d. We'll get to that in just a minute. Okay, let's do one more example just to make sure that you've got this. Let's move our eyes to the right. Let's do arsenic, which is right there. Okay, so again, they always start the same. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, you've got a big number 4 there. It goes back to 4, 4p3. Okay, and again, we'll talk about why the numbers jump around like that. We talked about it in Chem 1, but we'll refresh your memory on that. Okay, in all honesty, we really don't go down into the F level. There are so many exceptions to the rule when you go down into the F sub level that it just, the AP exam has decided that they just don't even want to bother with that, which is fine with me. So just to refresh your memory, okay, these are just some more examples here for boron and nitrogen. In Chem 1, we had you write these arrows. It's called, this is called the orbital notation. When you draw the arrows, each arrow represents an electron. Okay, and let's just refresh our memories. Before we do some practice, I want to refresh your memory on some vocabulary. All right, so the big numbers in any electron configuration, the numbers represent energy levels. Okay, the letters S, P, D, F. Sorry, my handwriting's messy. Those represent sublevels, okay? When you see these boxes like this, okay, each box is called an orbital. We'll talk more about that in just a second. And of course, every arrow represents an electron. So just to kind of bring this all together, electron configurations do nothing more than tell us where electrons are located approximately, okay? So I'm going to give you some practice to do here, and the stop sign is there because I want you to pause the video and try coming up with the electron configurations on your own. Sorry, before you try these, there was that shortcut that I wanted to remind you all about. It's called the noble gas configuration. And let's just do potassium together. Okay, So if you look at your periodic table and you wrote out the electron configuration for potassium longhand, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, well, remember the noble gas configuration, you look at where your electron configuration ended and go backwards. What was the last noble gas in that configuration? And for potassium, that is argon. And we put the abbreviation, the symbol for that noble gas, we put it in brackets, and then we pick up from there. That's essentially saying, okay, we've done all of the configuration through argon. Where do we go from there? Then it's just 4s1. So there's our shortcut, our noble gas configuration for potassium. Okay, so pause the video and you guys try the rest of these on your own. All right, see how you did. Okay, and just so you guys know, on the AP exam, you may always use the noble gas configuration. They're never going to ask you to write it out longhand, although you certainly can if you wish. Okay, so just to refresh your memory on, a little bit of vocabulary, remember that the term valence electron just refers to the number of electrons in the outermost energy level. Anything else, all the other electrons, are called core electrons. And if you guys will recall, if you will remember back from Chem 1, okay, just by looking at where the element is, you can tell how many valence electrons it has, okay? Remember that everything in group 1 has 1 valence electron. Okay, all the elements in group 2, your alkaline earth metals, have 2. Most of your transition metals also have 2. And then from here, 3 valence, 4 valence, 5 valence, 6, 7, and of course 8 is the most number of valence electrons that you can have. Okay, so just wanted to make sure you guys remember that. Now, you'll be asked to do configurations for pure elements. You'll also be asked to do them for ions. And the reason I brought up valence electrons is because those are the electrons that will be removed first when you're creating an ion. Okay, so ions are particles that electrons have either been taken away or added. Okay, so electrons are removed or added from the valence energy level first. If we need to take more, then we can dip into the D sublevel. All right, so I'm going to do one with you first, just to make sure that you guys have got this. So we're going to do the strontium ion, the +2 ion. We're going to do that configuration together, okay? And what I would really recommend is that you write out the configuration for the pure element first, the neutral element first, and then look at taking electrons away or adding some. So the electron configuration for strontium is going to look like this. I'm going to write it above. It's got Kr, and then we pick up from there 5s2. Okay, now what does a +2 charge on an ion mean? It means 2 electrons have been removed. Okay, fine. Well, what is the valence energy level? It's energy level 5, and there are only 2 in there. So guess what? Those are the 2 electrons that I'm going to remove. So what does that leave me with? It leaves me with just krypton. Well, to write this electron configuration, it would be nice if we could just put Kr in brackets, but you can't do that. They're basically asking you to write the electron configuration for a noble gas. If you're ever asked to do that, you can't just put the noble gas in brackets. Unfortunately, you've got to back up to the one before it and pick up from there. And go all the way across, 4p6. So that is the electron configuration for that strontium ion. Okay, I want you to, actually, let's do one more together. Let's do this manganese +3. Let's do that one together. Again, I would recommend writing out the configuration for the neutral element first. So neutral manganese has a configuration like this: 4s2, 3d, 1, 2, 3, 4, 5. Okay. A +3 charge means 3 electrons are going to be removed. Now let's look at what the slide says. It says electrons are removed from the valence energy level first. Well, that's that one. 4 is a higher number than 3. So those are the electrons I'm going to take first. Gone. Well, that's only 2 electrons. I need to take 3. So look what the slide says. If needed, only then, because we've taken all the electrons from the valence level, only then can electrons be removed or added from the d sublevel. So this is a case where, yeah, I can do that. So this is going to come down to just 3d4. Let's clean it up a little. So AR 3d4. Okay. You guys do the rest. So pause the video, try the rest of them on your own, and then come back and check your answers. All right, let's see how you did. I hope it's legible. I tried to write as neatly as I could. So you'll notice here, guys, that a number of these ions have the exact same configuration. Like right here, strontium +2 and bromide -1, they have the exact same, their ions have the same configuration. And that happens. Okay, so if this is something that you find tricky at all, again, I would really recommend writing out the configuration for the neutral element first, and then looking at where do I need to take or add electrons. Okay, a little bit more vocabulary here. There are kind of some rules that you learned in Chem 1 about why electrons get put where they are. And the first one is the Aufbau Principle, which essentially says that electrons will fill in energy levels, sublevels, orbitals that are closest to the nucleus first, so lower energy orbitals first, before they start to fill in higher energy orbitals that are further away from the nucleus. And in Chem 1, we showed you this diagram a lot. You don't need it because these sublevels are on your periodic table in the correct order. Okay. I always think this slide is funny. It always makes me laugh because what I'm trying to say right here is that what I've illustrated here is the element helium, which has 2 electrons, but there's always somebody that reads this phrase here like some Shakespearean play or something, like, he with 2 electrons shall inherit the earth. I mean, I don't know. It just makes me laugh every time I put this slide up here. But what I'm trying to illustrate here is that helium's 2 electrons are in the lowest energy sublevel here in 1s. It would be a violation to have those electrons anywhere else. They will fill in 1s before they fill in anything else, which is why all electron configurations start with 1s. Now, if you'll notice on the y-axis here, it says increasing energy. And I want you to sort of move your eyes from bottom to top. 1s is the lowest energy. Then we have 2s, move a little higher, then 2p, then 3s, then 3p, then 4s. Now I know this is hard to see, but can you all make out that 4s is slightly lower on the y-axis than 3d? That is why the periodic table is organized so that 4s comes before 3D and then 4P is next, because, and this is the beauty of the periodic table, it is in energy order. 4S comes before 3D because 4S is at a lower energy content than 3D. So according to the Aufbau Principle, electrons fill in lower energy before higher, so 4S comes before 3D. Hund's rule is another one that you learned about in Chem 1. The sort of plain English version is that all electrons want their own orbital before they have to share. Okay, let me go back for 1 second and draw something for you. If you guys will remember from Chem 1, we drew, let's say I'm doing the element, let's say I'm drawing the electron diagram for nitrogen. So nitrogen has 7 electrons. I've got the first 2 already drawn, 1, 2, 3, 4, 5, 6, and 7. Watch how I draw them. Up, up, up. Okay. Those last 3 electrons will occupy their own orbital. Electrons are selfish. They don't like to share, just like we don't. Okay. They will have their own orbital before they have to share. If I go one more and I have 8 electrons in oxygen, now they've got to share. But Hund's rule explains why electrons, is observing the fact that electrons take their own orbital before they will share an orbital. Okay, the third and final one is the Pauli exclusion principle, which really is illustrated perfectly by this just drawing right here. An orbital, one of those boxes, can only hold a maximum of 2 electrons. A shoebox can only hold 2 shoes. Okay, and don't get cute and say, well, what if they're flip-flops? No, okay, just they're regular shoes. Okay, a shoebox only holds 2 shoes. And you know how you put shoes in the shoebox? You got to turn one of them so they're opposite. Electrons are not only moving around the nucleus, they're also spinning in place. Just like the planets. The planets, I always get these words mixed up, revolution and rotation. The planets revolve around the sun, but they also rotate in place. Did I get those backwards? No, I don't think so. Anyway, similar situation. And 2 electrons in the same orbital will always spin in opposite directions. Okay, this is real quick. I just wanted you all to know that sublevels have shape to them. The S sublevel is a spherical shape. And if you look at this, I didn't intend for this to be an optical illusion, but some of you may see this as a sphere. Others of you may see like you're looking down a tunnel. And now that I've said that, you can't unsee it. But what I'm trying to illustrate is that S sublevels are spherical. P sublevels are called dumbbell shape. Now let's think about this. Why are there 3 pictures? Because remember, guys, a P sublevel contains 3 orbitals. If you look at your periodic table, the p sublevel block, that area, is 6 electrons wide, 6 elements wide. A p sublevel can hold 6 electrons, 2 in here, 2 in here, and 2 in there. This is what the d sublevel looks like. Please don't ask me why that 5th orbital looks so different. I have no idea why. Okay, so d has 5 orbitals. F gets really weird. What? I don't know. Don't ask me to explain. F is super weird. I have no idea what's going on there. But all you need to know is that the F sublevel has 7 orbitals. It can hold 14 electrons. All right, so the last part of this, unit 1.5, has to do with Coulomb's law, and this is going to lead us into the next, our next subunit that we're going to talk about, which has a lot to do with periodic trends. Coulomb's law, which is what's written in black right here. Okay, I stole this image from another teacher. Theft is a crime. Oh well. But this is Coulomb's law. This little symbol just means proportional. So the force between 2 charged particles has to do with 2 factors. The charges on those 2 particles, like, are they positive? Are they negative? Is this charged particle not just +1, but is it an ion with a +3 charge? Okay, so Q1 and Q2 are charges, and R is the distance between them. And what this picture is illustrating is that when you have oppositely charged particles, they will have exhibit a force of attraction. Essentially, if you plug all these numbers in, if you get a negative answer, that means attraction. Okay. If, however, your charges are the same, they're both positive, okay, they will repel. Because if you multiply a positive number times a positive number divided by another positive number, if the force comes out to be positive, that means they will repel each other. Okay, now, there's 2, oops, let me go back up. So there's 2 things to consider here. Actually, I will go here. So let's look at this diagram one more time, all right? And we're going to change some factors, and you guys are going to explain what, or I'll explain what the result would be. So we have these 2 oppositely charged particles, and the first question says, what happens if the particles have greater charge? Okay, so let's say these 2 particles are not just +1 and -1, but let's say it's +2 and -3. Okay, well, you don't have to change both of them, but the point is, if these numbers, these quantities are bigger, that's going to make the magnitude of the force bigger as well. So since these are oppositely charged particles, the greater the charge, okay, the higher that number is on both sides, the stronger that attraction will be. Okay, so that's the first thing to consider. The other thing is, what happens if the particles are further apart? Well, let's come back to Coulomb's law, that equation. That's going to affect this number in the denominator. If R is a larger number in the denominator, that's going to make the force a lower magnitude, a lower value. So those 2 particles, if I move them further away from each other, their force of attraction will not be as strong. So let's look at a sample question. Okay, and again, I stole this from another teacher. Shame on me. All right, it says, look at the diagram below. sort of a multiple choice question here, kind of. Which electron, A, B, or C? Okay, so they're asking you to look at this electron, or this electron. Which one is the easiest to remove and justify your choice in terms of Coulomb's law? And I just have put Coulomb's law back up there again for you to reference. So I want you to pause the video, think about it, see if you can come up with the answer. All right. So I'm hoping that you realized that C is the easiest electron to remove. And when we say easiest, we mean the one that is going to experience the weakest attraction between the two particles. Okay? C is the answer. Okay? Now, I imagine many of you would have gotten that. The tricky part is explaining it in terms of Coulomb's law. Okay? Now, let's just talk this out for a second. The difference between A and B, okay, same distance, all right, but A has a greater magnitude of charge there. So A is going to have the strongest attraction. Now B and C, they have the same magnitudes of attraction. It's +1 in both of them, and it's -1 in both of them. But the distance is the difference. Remember, the greater the distance, the weaker the attraction will be. So here's what I said. I said C has the lowest magnitude of charges and the greatest distance, thus the weakest attraction between the particles. Now, would they ever ask you to compare things where both quantities are changing? No, because on the AP exam, guys, you will not be calculating anything with Coulomb's law. It is all to do with just qualitative analysis. You're not going to be calculating anything. So you will often see Coulomb's law referenced, especially in free response questions. And it will very often be referenced in explain your answer using the concept of Coulomb's law. If you can write out the equation for Coulomb's law, great, but you still have to explain it. Okay, so that's it for 1.5. I hope you all have learned something today, and I look forward to seeing you next time.